Hey, everyone who's on, are you able to hear me okay?
Yes.
Okay,
Yes.
great, great. Hey, Srinath, I see you on there. How are you
Yeah,
doing?
good. Are you in the office or?
I'm in my office, actually reverse things so we get a little better lighting here, and hopefully the motion detector won't shut the lights off halfway through, although we'll be on PowerPoint most of this, so it'll hardly matter.
As people are joining in right now, it's about 20 people. I'm guessing we'll wait for 5 more minutes and then we can get
Sound
started.
good? So I've got the chat rolling in the corner here, so I'll be able to see the questions as they roll in during the presentation. And if there's a question of clarity, I'll be able to answer it. And we'll also have a record at the end.
So we are up to 40 people now. Another couple of minutes and then we get started. All right, in the interest of time, let's get started. I want to introduce our seminar speaker today, our very own Dr. Chris Vermillion. Chris joined the department 2 years back. He was an assistant professor at University of North Carolina, Charlotte, not far from here. Before that, much before that, he got all his degrees from University of Michigan. In fact, undergraduate was double majoring in mechanical and aerospace. And then he got his master's and PhD in electrical engineering, working on controls, control theory and applications. So he has some industrial experience with Toyota Engineering and also with Altacross and in Massachusetts. But he's been very successful in the past few years working on this interesting concept of using kites, wind turbines, tethered wind turbines. So he's going to share his research on that, and he's also been very good at putting together research teams working on different aspects of this. So Chris, take it away from here.
Well, thank you, Srinath, for that introduction. And by the way, if you guys have any trouble hearing me in the chat, just to shoot a message. I'm keeping a rolling chat log open here, so I'll be able to see those messages. I know there's a little landscaping going on outside, and also be able to see questions as they roll in. And let me know right now if there's any issues hearing. But let's get started here. So, like Srinath said, I'm going to be talking largely about my work, my lab's work, and collaborative work with other labs in the development of what we call ocean kites. Now, before I get started talking about that technology, I want to talk just a little bit more generally about what our lab focuses on. So we're the Control and Optimization for Renewables and Energy Efficiency Lab, or we call it the Core Lab. And I feel quite fortunate that I'm working at the intersection of what I consider to be two of the most important challenges facing not only the mechanical engineering community, but society at large, and that's energy systems on the left and autonomy on the right. So where do we fit in as a lab? Well, there are three big application areas that the lab is focused on right now, and some of you might have seen some of these applications before, but I want to introduce them for the benefit of everyone on the call. And by the way, thank you to everyone here who joined remotely. I noticed a couple people in the log here who were outside the walls of NC State, as far as places like Michigan, and then we also had the Outer Banks here. one of the silver linings, I suppose, with COVID is there is this opportunity for people to join in these seminars, and it's great to see you here. In any case, I want to talk a little bit about the applications that our lab focuses on. And you see on the left, one of those applications is using connectivity and autonomy to maximize fuel economy in connected and autonomous vehicles. And in the middle, an application where we focus a lot on, and in fact, a big part of this seminar is going to focus on, is tethered systems for wind energy and marine hydrokinetic energy. And the idea here, I'll talk about it more, is that by replacing a conventional tower structure with tethers and some lifting body, could be a wing, a kite, or an aerostat, you can harvest winds that are at much higher altitudes than you can conventionally harvest winds, and you can harvest marine hydrokinetic energy in waters that are deeper than where you'd be able to install a towered system. One of the newer focus areas of the research, and I'll talk a little bit about this at the end of the talk, is something I call renewably powered robotic systems. And this really represents an ongoing and future research vision that we got recent funding for. The idea here is to design mission planners and controllers for robots that are exclusively or predominantly powered by a renewable energy source. And it turns out that that paradigm really turns the problem of mission planning for robotic systems on its head. So before talking about the technical aspects of this research, I want to tell you just a little bit about my history. I'm not going to go all the way back to my birth. I'm not even going to tell you what year that is. You guys should probably figure it out. Won't even go back to my graduation, but I do want to go back before my time at NC State and talk a little bit about that history. I spent 3 years as a lead engineer at a startup company called Alteros Energies. Now it's called Alteros Inc. At the time, we were developing a lighter than air tethered system. You can see a couple prototypes here for harvesting high altitude wind. I took a lot of that know-how and my introduction to the renewable energy community and also my expertise in the control community. And I developed a lab once I took an initial assistant professor position at UNC Charlotte, focused on control and optimization tools for renewables and for energy efficiency. And the lab was fairly successful. You can see that graduated 3 PhD students before I moved over to NC State. And so we were successful in, I would say, that the niche area of applying control tools to renewable energy systems and energy efficiency in general. A lot of you might remember, those of you who were around when I interviewed back in 2018 for NC State, people asked, rightly so, what was my goal in joining NCSU? And at the time I said, well, what I really want to do is I want to start leading projects that are bigger than myself. You know, renewable energy is a multidisciplinary field by its nature, and control plays a big role. But for my renewable energy systems, so do aerodynamics or hydrodynamics. So does advanced dynamic modeling, and so does fabrication of large-scale devices. And so if we look at the rest of the timeline since I joined NCSU in the past 2 years, I think it would be fair to say that I've executed on that mission. And I'm very proud to have built a couple of extremely strong teams, and you see pictures of those team members here, that focus on some of these emerging renewable energy systems. These particular teams focus on tethered energy systems for marine hydrokinetic energy. And they bring together control expertise, but not only control expertise from my lab, also hydrodynamics expertise from the likes of Kenneth Granlund's lab, advanced dynamic modeling from Andre Mazzolini's group, and not only dynamic modeling and mechatronics, but larger scale fabrication, successful fabrication efforts from Matt Bryant's group. Now, make no mistake about it, we've still maintained our lab identity through this process here. And I'm very proud to say that we've published a number of papers, some of which have won a number of awards, graduated 4 students in the process. What I want to do in this seminar is sort of weave together that multidisciplinary, interdisciplinary work that we're doing and the specific control focus of our lab. And so let's zoom back in to my particular lab, the core lab. Again, I mentioned that there are 3 application areas that we really focus on. These tethered energy systems, both for wind energy and marine hydrokinetic energy, what we call renewably powered robotic systems, and then connected and autonomous vehicles. Now, in the rows here, I talk about some of the fundamental dynamics and control tools or topics that apply to each of these applications. And And in the middle, I talk about who's paying for the research as well. We're not going to have time to talk about all of these things, but I do want to talk a lot about tethered energy systems, specifically what we call ocean kites for marine hydrokinetic energy. And the fundamental topics, and you'll see these emerge, are number one, optimal control of repetitive processes. Turns out these types of systems execute repetitive motion, and we want to leverage that repetitive motion to maximize power. We want to optimally control these systems in spatiotemporally varying environments. The fact of the matter is that renewable energy resources, by their very nature, vary in both space and time. We want to behave robustly in that variable environment and leverage that environment as much as possible. And we'll talk about some of our experimental work as well. As a matter of fact, the outline for the talk looks a little bit like this. So I want to start by just talking about the motivation and the underlying principles for tethered energy systems in general, both wind and marine hydrokinetic, but really with a focus on marine hydrokinetic energy. And then I'm going to start talking about some of the adaptive control strategies and optimal control strategies that we've developed in the lab for ocean kite systems, and a lot of simulation results in ever more realistic ocean environments that we've put together. I'm then going to turn to some of the experimental work that we focused on, and I'm going to close by talking about this future, and really it's an ongoing research vision at this point, because we were recently fortunate enough to get some NSF funding on this future research vision in the area of renewably powered robotic systems. So let's get started here. So the focal point of this presentation is going to be developing control systems for what we call ocean kites, which are a marine hydrokinetic energy harvesting device. So let's talk a little bit about the resource. So based on estimates from organizations like EPRI and Georgia Tech, wave energy possesses enough power in the United States, the waters adjacent to the United States, to power 110 million homes. Tidal energy hits at 30 million homes. By the way, this is technical power estimates. So this is an estimate of power that could actually be harvested, not just the theoretical power. Ocean current energy, which is right in our backyard, adjacent to Cape Hatteras, can power 15 million homes. So this is a very, very large energy source. And by the way, in addition to the utility scale opportunities with marine hydrokinetic energy, there's what's called a blue economy. That's all of the off-grid applications in the ocean that require energy, and that's a $1 trillion economy that needs power. So why aren't marine hydrokinetic energy systems being adopted en masse? Well, for one thing, marine hydrokinetic technology compared to, say, wind and a lot of other renewable technologies is frankly in more of a nascent state. But I would argue that marine hydrokinetic systems, whether you're talking about wave energy or whether you're talking about tidal and current, are what I call burdened by bulkiness. And what do I mean? Well, you see some prototype wave energy converters and concepts here at the top of the slide. Well, generally they yield about 1 to 5 watts for every kilogram of mass that you put into the system. Now, we'll compare that with the ocean kite technology in a moment. We can also look at tidal turbines and conceptual ocean current turbines. Now, those function in principle the same way that wind turbines function. So they produce a power per unit area that's linearly proportional to density and proportional to the flow speed cube. So if you plug some reasonable numbers in, well, the good news for tidal energy systems that function on the same principles as wind turbines is that you can actually deliver a power density per square meter that's greater than a wind energy system, at least if you compare a 1.5 meter per second tidal resource or current resource to a 10 meter per second wind resource. The bad news is that, number one, you pay more per kilogram. Number two, because of the way that hydrodynamic loads vary according to velocity squared, the loads are higher for a given amount of power in marine hydrokinetic energy systems, so you need more kilograms. And the other bad news is this comparison is based on 1.5 meters per second. So what about all of the locations, particularly current resources, where that resource is lower than that? How do you harvest that with a reasonable amount of material? Well, that's where the concept of kites comes in. So the idea of ocean kites is to deploy a high lift to drag wing, that's what we call a kite, off of a tether, which is deployed either off of a floating platform or off of a seabed platform. the key principle behind the kite's operation is that it executes flight patterns that are perpendicular to the direction of the current, and these are very fast flight patterns, and they allow you to deliver marine hydrokinetic energy with more than an order of magnitude less mass and less size than the existing systems we talked about. So I'd like to talk just a little bit about the physics behind how these types of systems work. So let's consider just a really simple example here, where we have a wind resource or a current resource underwater, and we have a wing with some lift and some drag flying perpendicular to that resource. So that's the underlying principle behind kite-based flight. And it's flying at some velocity v sub c. The wind velocity, the flow velocity is v sub w. Well, the vector difference of the two is something that we call the apparent wind. And by definition, by convention, the lift force acting on the wing is perpendicular to the apparent wind. The drag force is parallel to it. Well, you can see two similar triangles here, and based on a simple analysis, and basically in this analysis is what's disclosed in a seminal paper, which was written way back in 1980, referenced by virtually anyone who's working on kite-based energy systems. The upshot of this simple geometric analysis is that the ratio of your flight speed to your wind speed or current speed is going to be equal to the lift to drag ratio. Now, why does that matter? Well, instantaneous power production is proportional to that apparent wind or that apparent flow cubed. So if you increase that through high speed motion, you increase your power significantly. And let's quantify it here. So there are two ways of actually generating the energy, harvesting the energy and delivering it to a customer on a kite-based system. One is what we call onboard generation. The idea here is that there are turbines that are on board the lifting body, in this case a kite, and you're delivering power down a conductive cable. The other type of generation is what's called ground-based generation. The idea here is that all of the electricity generation is happening on the ground, and it's happening as you unwind tether, as you spool tether out under very high tension. You obtain that high tension by flying in these perpendicular orbits. We call them crosswind or cross-current orbits, perpendicular to the flow. And then you expend a smaller amount of energy when you spool back in under low tension. You repeat that cyclically. As it turns out, the analysis for both of these types of energies works out to the same expression, which says that the mechanical power that you generate, there's going to be a conversion efficiency in here, but the mechanical power generation is going to be proportional to the lift squared over, the lift cubed over the drag squared. And these numbers with a well-designed wing can get well up above 100, increasing dramatically the amount of energy per unit mass that you're able to generate from a kite-based system. So it may be not so surprising that people have prototyped kite-based systems. So you see a few examples over here. Makani Power was formerly owned by Google. Google dropped them recently, which I'll let you be the judge of what's going on there. But Makani developed a tethered energy system, a wind system with onboard rotors. You can see that here, which executes circular patterns, very fast crosswind patterns, and transmits the power down to the ground over conductive cable. Kitegen's an Italian company. It's been around for quite some time, and they operate off of that second principle, ground-based generation, where tether is spooled out under very high tension and crosswind motions, and then spooled in under low tension. Ampix is a company out of the Netherlands that has designed a device that operates on the same principle. It's based on a rigid wing, but it still operates in that spool out, spool in principle. Minesto is developing kite systems, or a Swedish company developing kite-based systems for marine hydrokinetic energy. So they're executing those same motions underwater. And this is similar to, but not identical to, the thing that we're doing. They have, by the way, onboard rotors, a small ducted onboard rotor in this example. So where does our lab come in, and what are the key challenges that we're focused on? Well, for the projects that we're focused on, for the largest project at this point, we're focused on deploying a lightweight small kite off of a floating platform or a seabed platform with no rotating machinery on the kite. So we're using this spool in, spool out operation, which you can see here, spool out under high tension to generate power, spool in under low tension, and that requires a small amount of power. Now, Our lab's a control lab, and we're addressing a number of key control challenges, and there are a number of them. What you saw in the previous slides were based on a steady analysis. What can kites accomplish? Well, you still have to design a controller to actually execute efficient and robust crosswind or underwater cross-current patterns. There's all kinds of opportunities to optimize those patterns and also to optimize the power takeoff profile. In this case, the spooling speeds. When do you spool in? When do you spool out? And how fast? Now, there are some other big challenges, and this gets at why I've developed this multidisciplinary team with experts addressing all these challenges. But I want to focus today largely on the control challenges. So let's talk about those control challenges. So before I get into the details here, let me say that there are two cyclic control challenges that need to be addressed at once, really. And those are as follows. Number one, and you can see it in these GIFs here, the kite is always flying some cross-current flight path, and you're trying to generate as much power as possible, of course, in that flight path. And so what you want to do is optimize that flight path, which is clearly a repetitive process. The other thing that's repeating itself is spooling. You're switching between spooling in and spooling out. And again, your choice of when to spool in, when to spool out, and how fast has a tremendous impact on the power generation. So two repetitive processes, both of which have a tremendous impact on our overall economic goal of power generation. So before I talk about control, it's important to talk a little bit about the dynamic model. And by the way, and the design. And by the way, throughout the presentation up in the upper right, every now and then you'll see some headshots here. Oftentimes headshots of my students, Mitchell and Josh Daniels, a student who graduated, were my students. But in this case, we're very, very fortunate to work with a leading dynamicist in the department, Andre Mazzolini, and his student, Rodney Matoyer, in developing our nominal design and our dynamic model for the system. So here are a few fast facts about the system that we're going to look at here. It's got a fuselage length of 8 meters, a wingspan of 10 meters, a chord length of 1 meter. And it turns out that based on that system, you get a peak power at 1.5 meters per second of about 100 kilowatts. Now, by comparison, a fixed turbine with the same rotor area as the wing area here would generate less than 10 kilowatts. So, order of magnitude more power with the same amount of area. We have a dynamic model that we use for all of our control design and simulations that treats the lifting body, the kite, as a 6-degree freedom lifting body. It's neutrally buoyant, and that helps to enable efficient flight. It's controlled via control surfaces, so traditional ailerons, rudder, and elevators. We model the steady hydro using X-foil plus then a lift-induced correction. We also consider added mass terms, which are quite important underwater. And then the tether itself is modeled through what we call a lumped mass model, where the nodes of the tether represent concentrated masses, and then the links are spring damper elements that can't take compression because it's a tether. One of the unique features about our model, and it's pretty important, particularly in low flow speeds, is that we're able to characterize individual forces on the individual surfaces, and that means we can characterize the local flow velocities on each of the surfaces, which may be different because of spatial temporal variations in the flow. So I mentioned there are two control challenges, and they're both cyclic control challenges. And the first is, how do we define a flight path? And so I want to talk just a little bit about that. You see two sample flight paths here. One is an elliptical flight path, and the other one is a figure-8 flight path over on the right. Now, the idea here is the wind, or I should say the current, is coming from inside of the page here. So you're flying perpendicular to that current. By the way, this sphere that keeps getting larger and smaller here, that's what we call the instantaneous sphere. So at every point in time, the kite is flying on some sphere whose length is dictated by how much tether is spooled out. And the reason you see that size change is because the tether is being spooled as we're controlling the system. So in order to understand our tracking controller, and I could spend an entire seminar talking about the tracking controller, which, by the way, all of these students here, James Reed over here and John Borick, and of course, I introduced Mitchell and Josh, contributed significantly to this. The tracking controller is a hierarchical controller. It's got 4 levels to it. And to understand the basics of how we track a flight path, there's 2 angles to really understand. And they're on this slide here.
One of them we call the velocity angle. So the velocity angle, remember I said that the kite is always flying on the surface of some instantaneous sphere. Well, the velocity angle is the direction of the velocity. You can think of it as the heading of the velocity, which is a little different than the way the kite's pointing because it can be slipping, but it's the heading of the velocity on that sphere. And you can imagine you want to alter that to desired values as you traverse a path. The second value, which is extremely important if you're off the desired path and want to get back on it, is what we call the tangent roll angle. That's the angle between the horizontal axis of the kite and the tangent plane to the sphere. And the idea here is that by rolling relative to that tangent plane, you re-vector lift, just like when you're banking an aircraft, and that allows you to begin to sideslip and get back onto the path. So the way the controller works is we take a prescribed path geometry. We'll talk a little bit more later about how we optimize that. Compare it to the actual, we compute a desired value for that velocity angle. At a second level of the controller, we compute a desired value of the tangent roll angle to get us back on the path. At the third level, we convert that desired tangent roll angle, based on how we're doing, based on feedback from the plant, to a desired moment vector, also taking into account our target angle of attack and our target sideslip angle. And the final level is what we call a control allocation module that uses what's called dynamic inversion to figure out what the required control surface deflections are to achieve that desired moment vector. So the other cyclic control challenge is, how do we take off the power? Well, in our work, we generate energy through spooling. We spool out under high tension to generate energy, and we spool in under hopefully significantly lower tension to get back to where we started, but we expend some energy doing that. So there's two ways that we can think about spooling. One is what we call multi-cycle spooling. The idea is that we spool over multiple cycles. You can see that instantaneous radius, that instantaneous sphere getting larger and larger and larger, and then spool all the way back in. In this GIF here, we retain that cross-current motion when we spool in, but actually we've developed a pretty robust transition controller since this GIF was generated that allows us to transition into and out of that cross-current motion so we consume as little energy as possible spooling back in. Second strategy is something we call intra-cycle spooling. And this allows us to keep at a relatively constant depth, relatively constant tether length. And what we do here is we divide each figure-8 path into spool in and spool out regions. We try to spool in at the more powerful portions of the figure-8 path and spool out at the more powerful locations, and spool in at the less powerful ones. And the way that we execute this is through a switching controller known as a state machine. So we have two states, two modes of operation in multi-cycle spooling. What we're doing when we switch between spool in and spool out is, very importantly, we're switching our angle of attack from an angle of attack that maximizes or generates very large CL cubed over CD squared, that quantity that dictates power output when we're spooling out, to a very small angle of attack when we're spooling in. And we do that based on tether length. Now with intracycle spooling, where we're dividing our flight path into spool in and spool out regions, well, we adopt that strategy of adjusting our angle of attack as well. We have to, because we want to be under low tension during the spool in. But instead of defining our transitions based on tether length, we do it based on predefined locations on the flight path. So I want to show you just a few simulations here in a constant flow speed, just to give you an idea of the power, the potential of kite-based systems before we go into some fancier results. So on the left, we have the results of an elliptical flight path. On the right, a figure-8 flight path. And what you're looking at here are the components of flight velocity. By the way, the flow speed in each case is 2 meters per second. It's in the x direction, so y is perpendicular to the flow. What you can see is in that 2 meter per second flow speed under, this isn't even an optimized controller, it's tuned, we're producing flight velocities of near a peak of 10 meters per second, nearly 5 times the flow speed. In fact, our maximum speed here is larger than, is 6.25 times the flow speed. And if we take a look at the power output, you can see the cyclic nature of the power output here. Power profile is shown in watts in these plots here. So you can see a peak power output of nearly 300 kilowatts for both the ellipse and the figure-8. Average power output is coming in just a little bit below 100 kilowatts. Again, these are unoptimized results and they're in a constant flow speed at this point. So at this point, we can ask ourselves a couple questions. One question, oh, I wanted to show one more set of results. I forgot I slipped this slide in this morning. Those previous results assumed an intra-cycle spooling strategy. So for every figure-8 cycle, we were dividing the cycle between spool in and spool out periods, sections. So what you can see is relatively rapid periodicity with a period of around 30 seconds between the spool in and spool out. Here's some results where we're doing multi-cycle spooling. So we're spooling out over multiple figure-8s, suspending our cross-current motion and then spooling in, and then repeating the cycle. And we actually generate a little bit more power here, over 100 kilowatts, 122 kilowatts in that 2 meter per second flow. So now I would like to talk about a couple of other questions that we might ask ourselves. So we might ask ourselves, okay, we figured out how to generate robust, at least in a constant flow, cross-current motion out of the kite. Well, how can we optimize that cross-current motion? And so we're going to look at that. And remember, there are two things that ultimately we're seeking to optimize. There are two repetitive processes in particular. There's the path following process, or the path planning process, where we can fly a different path every single lap. And then there's the spooling process as well. And I would say that there are two broad classes of tools that we can use for this optimization. One class of tools comes from the optimal control community, the classic optimal control community, where we use tools like calculus of variations and Pontryagin's maximum principle. Some of you might have learned it as Pontryagin's minimum principle, but in this case, we're trying to maximize a lap average power output. We could use those tools in conjunction with a model of the system, a dynamic model of the system, to optimize our flight path or our spooling profile offline. The other thing we can do is, since this is a repetitive process, we can use learning. We can learn from one iteration to the next using tools like iterative learning control. Now, I refer to the tools that we're going to talk about here for learning as economic iterative learning control. The reason being that instead of just trying to track a prescribed reference, a prescribed path, well, what we're trying to do is we're trying to optimize that path, and we're trying to do so in pursuit of an economic goal rather than just tracking a prescribed trajectory. So which tool you go with kind of depends on the nature of the problem. If you have a really good model and a simple model of the system, you can use offline optimization. You'll get a solution that you can implement immediately. But if you don't have a perfect model, if that model is very, very complex, well, incorporating learning becomes important. And in fact, when we look at the path optimization, we've decided to take that learning approach. What we've done is we've tailored tools from what's called iterative learning control, which basically applies feedback control laws in iteration domain, where an iteration in our case is the lap of that figure-8 cycle. We've taken tools from iterative learning control and applied them to the goal of maximizing a performance objective. So traditionally, iterative learning control, sometimes called ILC, by the way, is focused on just tracking a prescribed set point and tracking it better and better as the iterations progress. We want to maximize a power output. So here's the basics of how we do it. We perform an iteration, that's a lap. We measure a reward, that's a lap average power, indicated by the light bulb. We update an estimated response surface. And so we keep a running estimate of how our reward varies as a function of the shape of that flight path in our case. And we define the flight path, by the way, based on a course height and a course width. Apologies that that's very, very small here. And then we update our path and update our control trajectory to track that path. And we perform another iteration. And if what we do works, that reward will increase and increase as time goes on. So let me talk a little bit about some of the underlying details. And there's really two underlying details that are important in this approach. So one is that response surface estimator. We are keeping a running estimate of how our performance, we call that performance J. So that's a lap average power output in our case. That's what you see down here. We're keeping a running estimate of how that depends on the parameters that describe the path. And we're using that running estimate, in our case based on a gradient, but you can also use other adaptation laws. We're using that estimate in order to adapt at every lap the shape of that path. So in terms of a block diagram and in terms of how that lap-to-lap adaptation, that iteration domain adaptation mates up with the hierarchical control that I talked about earlier, well, this gives you an idea. So the iteration domain, or the lap-to-lap learning, utilizes J, which is a performance index. It's our lap average power. And the ultimate output of that iteration domain adaptation is a set of waypoints. It's a geometry that describes the path. And that geometry is passed then to our hierarchical controller, which operates in the time domain. So this action is taken at the end of each lap in preparation for the next lap. So how does it work? Well, here's an animation where you can see a kite flying figure-8 profiles. By the way, flow speed is a 1 meter per second flow speed with a tether length of 125 meters. What you see on the right here is the lap average power. And what you can see is as the laps progress and as the path geometries adjust themselves from lap to lap, that power output increases and increases and increases. By the way, side note about this, you can see little tails in this simulation here that turn from green to red. We're doing what I called before intra-cycle spooling here. So the green corresponds to regions of the flight path where we're generating energy by spooling out, and then the red corresponds to regions where we're requiring energy by spooling in. So here's just a plot of the lap average power as a function of time. And you can see we go from just over 20 kilowatts to over 40 kilowatts in that particular system and that particular flow speed. And this is over laps. So this just gives you an indication essentially of how long a lap takes if you divide the amount of time by the number of laps. And we're in the 40-second or so regime for the amount of time a lap takes. So the other thing that we're interested in optimizing, remember there are two cyclic processes at play here. The other thing we're interested in optimizing is the spooling profile. When do we spool in and require power? When do we spool out and generate power? How fast do we spool in? How fast do we spool out? So this work was led by an undergraduate, an excellent undergraduate of mine, Josh Daniels. Unfortunately, he was an ROTC student. I say unfortunately, not because I have anything against ROTC, but because we lost him to actually to the Space Force. He didn't choose the Space Force, depending on how you feel about Space Force. That could sway you one way or another about him. But he was an excellent student who devised an optimal control strategy for spooling. And one of the things that he noted in terms of spooling is that even though our dynamic system is relatively complex, you can pretty accurately characterize tether tension over the course of a figure-8 flight profile as a function of two things. One is the spooling speed, and the other thing, which is along this axis over here, is the path position, which varies from 0 to 1 as you fly a path. So just dissecting this a little bit, because it's really the basis for this optimal control study here, just dissecting this a little bit, as you might expect, as you're flying a figure-8 path, which is assumed in here, your tension as you fly the path for any given spooling speed is going to rise, and it rises during the straightaways of the path, by the way, and then it's going to fall toward the edges, and then you get to a straightaway again, and it rises and falls and rises. Now, the other thing that happens is as you spool out faster, you decrease the tension in the tether, and you see that as you look at the spooling speed axis. There's one other weird thing. There's this dramatic jump at a spooling speed of 0. That comes from the fact that in our switching controller, we're intentionally adjusting the angle of attack when we spool out versus when we spool in. So when we switch to spool in mode, we intentionally operate at a lower angle of attack to require less power on the spool in. So that's the reason for the significant switch. So it turns out that based on this simple model, something we call a meta model, we can use a very classic tool from optimal control called Pontryagin's maximum principle in order to derive what I think is a very elegant form for the optimal solution for spooling and power takeoff. And there's a very graphical interpretation to the result that you get from Pontryagin's maximum principle. So I won't get into all the details of Pontryagin's maximum principle. It comes from calculus of variations, requires you to set up what are called state and co-state equations. Because of this simple meta model, by the way, we only have one state variable for the tether length, and therefore only one co-state variable. And the whole thing is predicated on something mathematically called the Hamiltonian. But, if you're an optimal control theorist, that's all interesting. But if you're just interested in power in general, I think the geometric interpretation of the optimal strategy is interesting to a broader community. And that's this. Look, if we weren't constrained to spool in as much as we spool out, So we place a constraint in our optimization that over every lap, we have to spool in exactly as much as we spool out. We have to get back where we started. If we weren't constrained, we would just spool out, and we would spool out at the speed that maximized tension times spooling speed, mechanical power, if we don't take into account conversion efficiencies. So that would be graphically equivalent to maximizing the size of a rectangle where the origin is down here, and or the bottom left corner is down there, the bottom right corner is up here. Well, it turns out when we do impose a spooling constraint, what we call a net zero constraint, well, there's some critical tension. That corresponds, again, if you're an optimal control person, this will be interesting, to the value of the co-state, which you can determine to be a constant. And there's a geometric interpretation to the best spool in or spool out speed. It's the speed that maximizes the size of this rectangle. And the optimal spool out speed maximizes this rectangle size. The optimal spool in speed maximizes this rectangle's size. And which rectangle is bigger dictates whether you should be spooling in or spooling out during that segment. So here's a segment. What you see over here, by the way, is a slice of that three-dimensional plot. Here's a segment where we should be spooling out. Here's the speed. Here's the tension that we're going to get. Here's a segment taken during one of those troughs, one of those points where the tension is pretty low. Well, that's where we want to spool in, and that's reflected, in fact, in this geometric interpretation. By the way, this was presented at the IFAC World Congress just over the summer. So as a result of this strategy, well, you can see for a flow speed of 1 meter per second, 125 meters tether, well, you can see anything in general from a 15 to a 45% improvement in power output. This particular simulation yielded a 26% power improvement. And you can see the differences between the optimal and a simple heuristic spooling strategy here, where the optimal strategy, by the way, the kite is flying in this way here, an optimal strategy delays the onset of the spooling, and it also varies the spooling speed over the course of these corners of the figure eight to produce significantly more power. So one other thing that we've done, you could ask yourself, well, how does this kite behave? Every result that we've taken a look at so far has focused on a constant flow environment. How robustly does the kite behave in variable flow? After all, I mentioned at the beginning of the presentation that any renewable energy system, at least any flow energy system, is going to be characterized by a spatiotemporally evolving flow resource. Well, we characterize that spatiotemporally varying resource in a marine hydrokinetic domain, and this is work led by my student James Reed, and we were very, very fortunate to work with an excellent oceanographer at the ECU Coastal Studies Institute, Mike Mulia, very photogenic as well with his pictures here. So the way we consider this spatiotemporally varying flow model is, remember I mentioned that our dynamic model characterizes each hydrodynamic surface separately. And so it's able to characterize the local flow velocity at each of those surfaces, which can be very important, especially in low flow when there's a significant time delay between when the wings, for example, see a change in the flow speed and when the stabilizers see a change. There's also usually a difference in the flow speed along the tether, and we're able to characterize all of the local flow speeds there. So what we do is we pass those fluid dynamic centers into a flow profile model, and that flow profile superimposes a mean flow and a high frequency turbulence. And let me just show you a little bit more about that over on this slide. So the mean flow field is modeled as a function of depth. So this y variable here is the cross current location. So the flow is going into the page here. So this mean profile either comes from models, or where we have it available, it comes from acoustic Doppler current profiler, or ADCP data. Now, we superimpose on top of that model a spatiotemporally varying turbulence. We use a turbulence model that was developed at Florida Atlantic University. And what you can see here, again, the perspective is the same. The flow is going into the page. What you can see here is just the turbulent component, which is either adding or subtracting from the main flow. And you can see this elapsing over time. And what that results in is an overall flow field where, again, we're able to present the local flow velocity to each one of those hydrodynamic surfaces on the kite. So here's a couple of GIFs that show both elliptical and, both figure eight and elliptical cross current motion. These are both using that intra-cycle spooling. in the presence of that varying flow profile. And what we can see are a couple things. Number one, robust operation of the kite in spite of the variable flow. And also robust performance in terms of the fact that you've got, on average, a 1.4 meter per second flow speed. You can see that you're easily flying 4 or 5 times that flow speed at peak. Here's some graphs, by the way, that show the local flow speed at the kite and also the kite speed in a snapshot of those simulations. What you see here is periodicity in both the local flow speed and the kite speed. You see that some of those high frequency variations in the local flow speed are filtered by the closed loop dynamics of the kite. You see that factor of 4, factor of 5 velocity augmentation. You also see this periodicity in the flow speed. Now, this is not the kite speed, it's not the apparent flow speed, so it has nothing to do with the kite's speed, it has to do with the kite's location. So when it's flying these figure eights, its depth is varying, so it's varying its location in what we call the shear profile. That's changing the local flow speed that we're seeing. By the way, this work was presented at IFAC World Congress. James led this work, and he's actually got a journal paper in renewable energy under review. So I want to talk a little bit about our experimental work. We don't just do simulations in our lab, and with these larger projects, we're going to be able to do larger scale experiments, which is something we're very excited about. But one of the hallmarks of what we've developed as a lab, and those of you who were at my presentation when I interviewed at NC State know a little bit about this, is we developed an experimental setup, a lab scale experimental setup, where we literally 3D print, tether, and fly models of tethered energy systems in a water channel environment to investigate their flight dynamics. And this started even back before I became a faculty member, back with a partnership between Alteros and University of Michigan. At the time, we weren't doing any closed loop control, so we were just examining passive flight of the system. We migrated at UNC Charlotte to a closed loop system where we could both characterize the dynamics of the system and also control the system. So what you see here are high-speed cameras. Those are obtaining real-time images of the system. We have tracking markers on the system here. And then little DC motors, micro DC motors that are modulating tethers. We use tethers to actuate the system in the water channel environment. And all of the control is being done on a high-performance target computer. Now, since UNC Charlotte, we've migrated our system and improved our system. We've migrated it over to the NC State water channel, and we've been very, very fortunate to be able to work closely with Kenneth Granlund and improving that system and running additional experiments. This just shows that target computer stack that we use. Now, what's the purpose of these experiments? Well, the ideal result of these experiments is to produce what we call dynamically similar behavior to full-scale tethered energy systems. That is, for some of these small 3D printed models, we want to observe dynamics in the water channel, and we want to be able to say with confidence that the dynamics of the full-scale system will replicate those dynamics. That can be a tall order, in particular because of, number one, a Reynolds number mismatch between the water channel and the full-scale system. Number two, the fact that just from an engineering perspective, there are certain things you can't do in the water channel. With these small models, it's virtually impossible to instrument the system with control surfaces, for example. So we use tethers, but tethers are different than control surfaces. We're space limited. We have limitations in terms of the flow speed. But what we can do in those limitations where we can't actually produce dynamically similar behavior is what we can do is validate and refine our dynamic model. After all, our dynamic model can be scaled to the water channel scale. Our dynamic model works with multiple tethers and tether actuation. It works with control surface actuation as well. So we've taken both approaches over the years. It's interesting to ask the question, well, under what conditions will those lab scale experiments, and by the way, these 3D printed models are roughly 100th of the full-scale system, depending on how large you scale the full-scale system. It's interesting to ask the question, well, under what conditions will the lab scale results match full-scale? Well, we did a dimensional analysis of this, and this was published, by the way, in AIAA Journal back in 2017. So this is work from back at UNC Charlotte to determine the answer to that question. And the answer to that question is, if we want to preserve dynamic similarity, we have to do a few things. In addition to having uniform hydrodynamic or fluid dynamic coefficients at both scales, we need geometric similarity. Everything needs to be scaled by the same length. We need to maintain similarity in terms of net buoyancy. And finally, we need to preserve something called the Froude number. And this is something, again, that comes out of a Buckingham Pi-based dimensional analysis. This wasn't just speculated by us. It turns out if we do those things, we get a really neat result. And that is that the dynamics at scale will be the same as the full-scale dynamics, except for the fact that all of the time constants will scale according to 1 over the square root of the length scale. What does that mean in practical terms? It means if I fly a 100th scale model in the water channel with similar hydrodynamic properties, well then I'm going to get similar dynamic performance, except for the fact that my time constants are going to be 10 times as fast. As a matter of fact, we validated that through some experiments on 3 different models of 3 different sizes. We chose models that exhibited what are called limit cycle oscillations. Those are oscillations where no matter how small a perturbation you make to the system will start to undergo oscillations of the same size, regardless of whether that perturbation is large or small. And that allowed us to overlay plots of things like heading angle and other variables against non-dimensionalized time and against time. And what we can see is the plots do in fact overlay, fulfilling that hypothesis that the time scale is going to go as the square root of the length scale. We extended these results to closed loop crosswind flight. We first focused on these models over here. By the way, these models here, you might recognize them. They're models of the Alteros buoyant airborne turbine, a lighter than air tethered system. It doesn't fly great crosswind or cross current flight, but that wasn't really the point of this analysis. The point of the analysis was to extend our dimensional analysis to control variables and to show that if we scaled those control variables according to Buckingham Pi, once again, we would get dynamic similarity. And you can see that in comparing the dimensioned and non-dimensioned time results here. This, by the way, was published in Dynamic Systems Measurement and Control in 2017. And more recently, I've worked with Kenneth Granlund and then 2 of my students, Ayaz Siddiqui, and very recently Karthik Naik, a new student of mine, to extend these water channel results to a kite system. Now here, the kite systems that we're modeling are quite small, and the chord length of the wing, which really is the relevant length in calculating Reynolds number, makes for a Reynolds number that, depending on your flow speed, can easily be less than 10,000. And so it's very dangerous to say, well, if we hit all those dynamic similarity numbers, we're going to have similar flight to full-scale flight. There are differences. What we were able to do, though, is take our dynamic model, scale our coefficients down to the water channel scale, and compare model results against the experiments. And what you're looking at here are roll angle, the lateral position of the kite, and the lateral velocity of the kite. I'll go ahead and play a little video here of the thing flying in the water channel. And again, we're not going for, in the water channel, super efficient flight. What we're going for is making sure that our model is accurate as we go to larger and larger experiments. Speaking about those larger experiments, we are in the process of setting up the experimental system for doing pull-based tow testing in the winter of 2021 of a kite system. This system will be about 1/20th scale. It'll be large enough to accommodate control surfaces. It'll operate at higher Reynolds numbers. It'll give us a better indication of the real-life implications of the control strategies that we're pursuing. And then we're going to be moving, with the help of Mike Mulia's group and Coastal Studies Institute, to open water tow testing, where we're going to be taking one of their research vessels. We're going to be instrumenting it with a winch and spool and a tether angle sensor for measuring the position of the kite, actually flying a kite, or the goal is an hour of uninterrupted operation in Lake Norman of North Carolina. We're working on the permitting for that right now. So I want to close with a very short section, just 3 slides or so, to talk a little bit about a future research vision, which I think is a very bold, very exciting area of research. And it's what I call renewably powered robotic systems. So let's look at a couple of systems to get an idea of what I'm talking about here. What you see at the top is what's called a sailing drone, or an autonomous sailing robot. This one is produced by a company out of Alameda, California called Saildrone. The idea of an autonomous sailing robot is to replace some of the operational capabilities of traditional oceanographic and atmospheric research vessels, which can run as much as an operational cost of around $1 million a month to operate. And so this is a big, big accomplishment if autonomous sailing vessels can replace some of those very, very expensive research vessels. And the idea here of the sailing drone, and by the way, they've demonstrated robust operation over thousands of miles at a time in pretty rough places like the Bering Sea and the North Atlantic. The idea is to carry out persistent missions, persistent climate change observation missions, persistent oceanographic observational missions, because you're powered by this perpetual resource wind. Another project, this is a project that we're actually working on as part of a DARPA team. I'm working with my colleagues, Andre Mazzolini, Kenneth Granlund, and Matt Bryan on this one. It's called the Manta Ray Project. The idea is, well, the idea that our team is pursuing, the idea of the program is to develop very long endurance, very high payload, autonomous underwater vehicles. Our concept is, and it's shown over here, is to develop a glider that's being developed by a partner of ours, a defense contractor partner of ours, that can periodically park itself on the seabed and deploy an energy harvesting kite. Operates in the same way as the kites I've been talking about, and that energy harvesting kite can recharge the battery on the glider and allow it to pursue ultimately a very long endurance or even a persistent mission. So when you look at these renewably powered robotic systems and you compare them to, say, wheeled mobile robots and quadrotors, I would make the argument that renewably powered robotic systems turn on its head the paradigm that's faced by most robotic systems. What do I mean? Well, most robotic systems are faced with finite range, sometimes very limited range, which make missions in hostile environments almost impossible. But they do have fairly predictable mobility, meaning given a set of waypoints, I have a pretty good idea when I'm going to reach those waypoints. Well, renewably powered robotics turn that on its head. Renewably powered robotics have very large range, even infinite range, but the mobility is stochastic. And because of the mobility is stochastic, that demands a fundamentally different control strategy and mission planning strategy. Just to give an idea, a graphic idea of why that is. Normally you prescribe a mission through a set of waypoints. Well, if you do that for a renewably powered robotic system, you don't know when you're going to hit those waypoints. Because you don't know when you're going to hit those waypoints, it's not possible, at least in a deterministic sense, to prescribe a set of waypoints that are going to complete the mission in a time optimal way, because you don't know when you're going to hit the waypoints. Now you could say, okay, I'll just prescribe search directions. I'll just say at each time, I'll prescribe a direction where I'm going to go. Well, then your time step is fixed because you made it fixed, but you don't know how far you're going to get in those search directions. So it turns out we've done some initial work toward this. In fact, we recently got an Nsf grant where we're focused on sailing drones as an application. We're actually building some robotic sailboats, a small fleet in the lab. You can see some of our composite layups. So we do some fabrication in the lab. It's not just control design. One of the things we've done in the meantime is we've taken our sailing drone design, we've characterized what's called a velocity polar. That tells you how fast the sailboat is able to go in any direction relative to the wind. We've used something called stochastic dynamic programming in order to perform what's called a Monte Carlo study, where we simulated the performance of that sailboat under that optimized control strategy in an upwind race under different levels of volatility. And that's what you see over here. By the way, this was published in the American Control Conference. We've also done some initial work in terms of optimal charging strategies for that combined autonomous underwater vehicle and kite system, the system where the AUV either anchors itself or parks itself at the seabed and then deploys the kite. Now, by deploying the kite at strategic locations where you have a greater flow resource, and we do that through dynamic programming, we've actually extended that to something called stochastic dynamic programming, you can shorten the mission time, and you can see the shortening of the mission time in the bottom right. So that brings me to the close of this presentation. And in closing, I'd like to just say, we're living at a time of what I call revolution in both autonomy and energy. And so we need bold solutions. And solutions like Ocean Kite, solutions like renewably powered robotic systems represent some of those bold solutions, which I think will drive a very bold future research program. And I'm so thankful to be part of this department and to be able to be contributing that future research program to the department. So with that, thank you for your attention. Happy to take any questions.
All right, we have a few minutes for questions. If anybody wants to type in the question, I'll read it out in the chat rather than making everybody talk on that. So just type in your question, and I will read it out to Dr. Vermillion so he can answer the question.
And I'm monitoring the chat as well. So
that's right. That's right. All right, faculty, you want to ask a question? Chris, you are very, very detailed here. Yeah, the recording and the live slides will be available. We don't know for we certainly make it available for faculty. There is a question from Ashok.
Yep. So the question was, how does the kite operate in a stall regime? So that's a very good question, and we haven't done a really detailed investigation of stall. One of the benefits, though, of our kite is we've got a neutrally buoyant system, and as a result of that neutrally buoyant system, at least for the marine hydrokinetic kite, it's significantly easier to recover from the stall. Although the preferred solution by far is to avoid that stall regime altogether. You know, the one thing that I would point out as well, just to get more wonky, I think Ashok may appreciate this, is that optimal power delivery, and this gets at a trade-off between robustness and performance that can be managed through control. The optimal power generation of a kite-based system goes as the CL, the lift coefficient cubed, over the drag coefficient squared. And what that ultimately means is the optimal angle of attack is going to be beyond the angle of attack that maximizes L over D. So it's going to be closer to the stall point. And in fact, there are a lot of kite-based systems where that optimal angle of attack is very close to the stall point, and you run the risk, particularly in a lot of dynamic maneuvering, of tip stall. And so there's kind of this trade-off between the margins that you incorporate in the controller and the robustness of the controller. You want to back off a little on the angle of attack, but you pay a price there in terms of robustness. It's something that we're managing these days. Xiaoming asks, how about the efficiency of the ocean kite in compared with wind turbine and ocean magnetic generators? So the thing that I like to look at in terms of efficiency is levelized cost of energy. And so that's just for the general audience perspective, that is measured in dollars per kilowatt hour. It's the cost of energy per amount of energy you generate amortized over the lifespan of the device. So in comparison with the two, in comparison with wind turbines, well, we're tackling a different resource, but wind turbines have undergone a dramatic decrease in cost over the past 2 decades, from being in the teens in cents per kilowatt hour to being in the vicinity of or less than 5 cents per kilowatt hour. And we're still not there yet in terms of the kite-based systems. However, the estimates that we have, particularly at the utility scale, say that we'll be able to get well under 10 cents per kilowatt hour and close to 5 at maturity. So we're comparable enough with wind turbines, at least with the kite system. And I don't know of another marine energy technology that's able to hit those targets, that's purporting to hit those targets. And so those targets are important because although we're targeting a different energy resource, in order to be cost competitive at a larger scale, at a utility scale, or in a lot of even off-grid environments, we have to have get that LCOE down. So those are kind of the numbers that I'm aware of.
I have a question for you.
Yep.
Say I have a rural farm which is 100 acres, and I'm the only person living there, and I want to be off the grid in terms of energy production. Could I have and I'm living in an area where there's high wind. Could I have one of these kites up there to generate distributed energy for my own system, for my own farm and my land? Is it something
Sure.
that you see that as a potential opportunity there?
I think that, yeah, so those small scale opportunities are not only, I think, potential opportunities, but they're key opportunities to act as stepping stones to larger scale and utility scale adoption. Now, I don't think the appropriate the appropriate customer to go after would be, well, I could be wrong, but it's probably not individuals or owners of a small farm, just because they're unlikely to adopt the level of risk that's inherent at this level of the technology. I think the people to really go after are, number one, people who are just paying a premium for the alternative source of energy. So if the alternative is diesel fuel, as it might be if I'm an off-grid customer, I want to look for the customer with the highest risk tolerance. And often the customer with that highest risk tolerance is a customer like the military or a customer like offshore oil and gas and exploration. But you're absolutely right, in my opinion, that the key way to advance these kind of high risk, high reward technologies is by using the off-grid, the niche markets as stepping stones. In fact, the DOE has really focused on that in terms of its water power technologies office focuses over the last few years.
So I'll share it out with the last question. I'm pretty sure. What about extreme weather situation? What happens when you have an event that you really cannot operate this thing at?
Yeah. So there are a lot of opportunities with the marine hydrokinetic systems, particularly if spooling is an option to alter the depth. So usually always to some extent, the impact of surface waves diminishes pretty rapidly as you get significantly under the water. In fact, my student James Reed did an excellent study, it's under review right now for renewable energy, but one of these days I'll present it to the group, where he analyzed the robustness of the performance of the Kite in a lot of extreme wave events, which arise from extreme weather events, and these were driven by actual buoy data. And what he found was performance is highly sensitive to the operational parameters, particularly what depth you're operating the Kite at. But you can obtain a significant level of robustness if you're smart about the operation of the system. By the way, it's trickier for wind energy than it is for marine hydrokinetic energy. There isn't a sea that you can live under in that case.
All right, so we're going to share. Oh, there is a question from Andy here. Okay, go ahead.
Yeah, so the question is, does turbulent flow field induce stall locally on the wing? It's an interesting question. So I think the question drives at the fact that with this turbulent flow field, we're superimposing a turbulence, which could be in any direction, and it's got components in all directions on top of the base flow speed. And because of that, the local angle of attacks can be quite high. So it would be interesting, actually, I haven't done this, but maybe it would be something for a student to do, to go through with a fine-tooth comb the simulation results and actually flag, in the presence of turbulence, the instances where the local angle of attack for some period of time exceeds the threshold for stall. What I will say are a couple of things. Number one, because we're simulating marine hydrokinetic systems that are neutrally buoyant, again, the stall recovery is relatively easy. So we may, in fact, be in transients getting some of these high angles of attack and muscling through them, so to speak. The other thing I would note is the faster we're flying the Kite, the smaller the impact of those turbulent variations, simply because they're being superimposed on top of an apparent flow speed, well, on top of a flight speed that's very, very high. But it'd be an interesting thing to look at more deeply. Thanks for the question. Very interesting question.
All right. In the interest of time, I'm going to close it down here. And thanks, Chris. It's a wonderful talk, and it was really good to see where you're headed in this last 2 years, especially after coming here. And of course, the team is really of value. If anybody is interested, our newsletter will be coming out, and there will be a feature on the team that Chris was talking about, the 4 faculty members. So a little bit more insight about their research and where it's going. So if everybody is interested, maybe in a couple of weeks, you will see it on our website, the newsletter, which will have an article on this topic. All right.
Well,
thank you all for coming in. Yeah, go ahead, Chris.
Thank you. And by the way, for anyone who has additional questions, feel free to email me, reach out, and I'll do my best to answer those questions. Very interested to hear what you have to say.
All right. We're going to shut it down, and thank you. And thank you again. Next semester, next week, we have another seminar, so we'll watch for the announcement.
And here's what I look like, by the way, for everyone.